All right, let's talk about a difficult subject that typically students have a problem with in understanding a weighted average as far and atomic mass and relative atomic mass. It's kind of difficult for us to understand this concept, so kind of bear with me. We have to have a way of talking about the mass of these elements, obviously, because we need to work with them quantitatively in lab. And there are several things that lead us to being able to work with them quantitatively in the lab. And we have to start somewhere, so we're going to start talking about relative atomic mass. Then we're eventually going to build our way into how we use the mole. Then we take the average atomic mass, and we use several different methods to actually quantify our experiments, leading up ultimately to our stoichiometric calculations. Now, let's talk a little bit about relative atomic mass. We have to have a way to make this mass kind of usable to us, and we can do that through some mathematical extrapolation of some measurements. The mass of an atom is expressed in atomic mass units, or AMUs, and it's called the atomic mass of the atom. The average atomic mass is what is displayed on the periodic table. Okay. We take up all the different isotopes. You know, we have several different isotopes, meaning they have different numbers of neutrons, and we add those together. Now, we base this upon the carbon-12, and the units we use are called atomic mass units. It's just some arbitrary unit that was developed to facilitate this. 1 AMU is equal to exactly 1/12 the mass of a carbon-12 atom. Remember, electrons are so small we negate their presence as far as mass goes, but we have to consider the mass of both the protons and the neutrons. Alright? So the average atomic mass, or the AMU, 1 AMU is equal to about the size of 1 proton, 1 neutron, is around about how we equate those. Now remember, the electron is 0.0005 times smaller than either the proton or the neutron. So we typically abbreviate and say 1 proton is equal to 1 AMU, 1 neutron is equal to 1 AMU. Now, we use this in calculations to calculate the average atomic mass. The average atomic mass tells us several things. It is a weighted average of all the isotopes. We have several different isotopes. For example, carbon, we have carbon-11, carbon-12, carbon-13, carbon-14. The majority of carbon exists as carbon-12, but we have a few trace isotopes, especially something like carbon-14, that we find very important as well. Now, when we find the average atomic mass, we're going to round it to 2 decimal places. Fortunately, this is already done for us on the periodic table, and you won't have to do this after this chapter. I want to show you where the chemists and physicists determine, or how they determine what number to put on the periodic table, and they get that as an average of all the different isotopes. So let's take a look at an example problem. That's going to be the easiest way for me to explain this, or actually let me explain the whole concept of a weighted average. Hopefully you understand this by now because we use a weighted average in this class, but the average atomic mass is equal to the mass of that isotope times its percent abundance, or how popular is it. For example, it would be unfair for me to weight a very hard grade much more than it would be an easier grade. So I like to kind of weight them evenly, just like it would be carbon-12 makes up most of the carbon in the world. So it makes up a good percentage, several percentage points of our carbon in our world. It would be unfair to take that kind of status away from it. So what we do is we use what is called a weighted average. So we take into account its abundance as well as its mass. So, and then to normalize it, or to take the average rather, we will divide by 100. So let's look at our first example. It says calculate the average atomic mass of oxygen if its abundance in nature is, and you're given the percent abundance, 99.76% oxygen 16, 0.04% oxygen 17, and 0.02% 0.20% oxygen 18. So now we take into consideration their percent abundance as well as their mass number. You should remember the mass number should be a whole number. So let's set this problem up. Oxygen 16, which is our mass number, has a percentage abundance or a percent abundance of 99.76%. We're going to add that to our next isotope, oxygen 17, which has a percent abundance of 0.04%. And we're going to add it to oxygen 18, which has a percent abundance of 0.20, and then divide it by 100. And we're going to get 16.00 AMUs. Now, this should match up with what is on the periodic table. And we look, and the oxygen on the periodic table says 15.9994. So we can safely assume that our answer was in fact correct. Let's take another example. Let's look at copper. Copper consists of 69.17% copper 63, which has an atomic mass of 62.94 AMUs, and copper 65, which has an atomic mass of 64.93 AMUs. Alright? So, how do we determine, let's go ahead and set our problem up. Copper 63 has a percent abundance, or copper 63, which has a mass of 60.94. This is a little bit more precise measurement. Has a percent abundance of 69.17 plus copper 65, which has an atomic mass of 64.93 AMUs. Now, how did we get that second percent abundance? Well, we can subtract from 100, of course, because we know that our percentages must equal 100. If we put that into our calculator, we get the average atomic mass of 63.55. We look over at copper on the periodic table. It says 63.546. Remember, we're going to use 2 decimal places in this class. Yes, this is how the scientists do it. They take into consideration the atomic mass and its percent abundance. Hopefully you can calculate this on an exam given the problem.